Great. So I think what I'm going to do here is, depending if you have the data handy or not, you can, if you do, you can follow along. If you don't, I'm recording this, and I also have the steps laid out in this walkthrough document here. That's also on Canvas under this assignment. Where we left off is we brought that Lidar data and the last data, and we were kind of visualizing it. Let me see if I can bring some of that up real quick. I also have a hillshade here. This is a hillshade from the digital elevation model. Let's take a look at that real quick. So this is 4x4. I'm assuming that's feet. I'll double check on that. Might be meters. No, so it's 4x4 and it's projected as UTM 12N. So that means it's 4x4 meters. That's the horizontal XY projection. Something that can be really confusing about DEMs is that if you look at this is the digital elevation model right here. I'll take the hillshades off real quick. So you can see that this is the original digital elevation model, and the raster values are elevation, right? Each little grid has a different elevation. Can someone tell me what the units are for the elevation of this raster? I'm just clicking on it and you kind of see the value right here of the pixels. And you can see the range right here. Are these elevation values in feet or meters?
Those are in meters, right?
So these are, 4,600 meters would be about 15,000 feet, right? In elevation. So this is feet. So you can have a raster that has horizontal projection in meters, and so the units in terms of X and Y and the cell size is all meters, but the elevation values are in feet, and that's a little confusing. It doesn't really matter, but you could also always convert the raster values of the cell values themselves to meters. And you guys remember how to do that? If I wanted to take this 4,600 to 4,500 and convert it to meters. What geoprocessing tool could I use? We would use the Raster Calculator. And so I just go to geoprocessing, Raster Calculator. And then this is just a very simple algebraic calculation. I put in this raster, if it ever pulls up. And so I could just pull this image in. Sorry, that's the DEM times, and then 3.281 or something like that, whatever the conversion is. And then that would just make a new raster. It would still have the same projection, but then it would be in meters instead of feet for elevation. So just something to keep in mind with rasters. Mostly, so, and I have this DEM in here just because I wanted to visualize it with a hillshade. I just bring that up again. This DEM came from the Lidar data. And so we're essentially kind of recreating the process to get from Lidar data, which is kind of that really coarse, I shouldn't say coarse, it's, you know, it's data, right? It's a bunch of points shot from a laser from an airplane. And it's important, right? We got to start with this, but it's not something we can use. And so the goal here then is to create this digital elevation model, incorporating the on-the-ground survey, that as-built survey. If you go to Canvas and download this homework data, let me just check what I put in there again. I didn't update it. I'm gonna, oh, that's the homework data. I'm on the wrong assignment here, sorry. Let's go to the lab. There we go. This data. I'm just going to double check what I put in there. Okay, so this on Canvas, you have aerial imagery, LAST data, the Lidar data, and then you have the points from our GPS survey. There's a survey area, and then there is the break lines. There are the break lines. So if you haven't done that, I do would like you to do that because it's, I think, good practice, kind of dealing with data and kind of getting it into a format we can use, but I did include those as well. All right, so let's get back to our steps here. I'm gonna just double check where we are. So last time can someone recall, kind of tell me what we did with the Lidar data? Just kind of the general idea. We brought the Lidar data in, we did some things to it. We did just a couple things to it. I'll call on Kalisha.
I know that we kind of looked at it in the 3D scene, so you could see that it had like elevation to it.
Yeah.
I know that we're intending to add our new points from our survey to the LiDAR as well.
Yeah, great. Yeah, so we did that 3D scene, and we did it through this view thing where we did a new local scene, just to see that it, yeah, like Kalisha said, that it has 3 dimensions to it. You can kind of see the river and the hill and all that stuff. The way it's colored as well, you can see that. The other thing we did, we had to create a LAST data sets, which is just basically like a geodatabase to contain it. And we did that in the catalog. So if I go to my databases, no, I think it was outside of the database, my folder. I created a, where is it? Created a LAST database, LAST data set. Anyway, it's right here. It's called .lasd. And it's just a way to import a bunch of tiles, basically, of LAST data. And then once you have that LAST data set, you can very quickly filter the data. And so I right-click on LAST data set. I have LAST filters, and I can just say, just show me the ground points. And that's what I've done already. And so that's why you can see, for example, the reflection of the river is out of there. It takes away any kind of buildings. It's usually pretty good. Let me just double check that we do that. And do you guys remember how we know how basically LAST data points are classified? They have kind of the data associated with them based on certain characteristics of what the thing on the ground the laser hits. Do you guys remember how we classified the data? or how last data is classified. I'll call on Tom.
It was like,
Ooh, sorry, Tom. How about Christian? Do you remember Christian?
I remember that we had like the ground points, but I don't remember.
How do we know that it's a ground point versus like a tree or something else?
I can't exactly remember that.
So the idea is you have different returns, and when a laser kind of goes from the airplane or whatever to the ground, it's hitting a bunch of different things. And it's kind of like a wide swath. Maybe it's like a couple meters in diameter or something like that. And so there's going to be different things that it hits on its way down. So it hits the top of the tree, it'll hit some leaves in the middle, it'll hit maybe the grass, and then it'll hit the ground. And all those things are little reflections that go back to the airplane in the sensor. And through what's called interferometry, the sensor is able to say, okay, here's the elevation of the first return, which is the top, the first thing that it hit. Here's the elevation of the second return or the last return. And the ground points are typically classified as the last return. Anything that came back last, we know typically, it's not going to be perfect, but that's going to be the ground, more or less. So that's the basic way that things are classified. All right, so let's get back to our progress here. We took the Lidar data and we made a 10 out of it, just using the very simple tool, or simple to use. I shouldn't say it's simple. We did last to 10, last data set to 10. It has to be in a data set. And so that's why we created that data sets. And if you forgot how we did that, that's in the walkthrough tutorial thing. And so this tool just allows us to put the Lidar data in, put it into a 10, and then essentially we did a clipping extent and then created that 10. So I'll show you what that is. Last time we ran into a problem because I didn't bring all the tiles in. And so if you download the data again from Canvas, it has 2 tiles now of last data. So that'll get us this side and then this side of the channel. All right, so I'm gonna take the Lidar data off. We have this 10. And you can see from the 10 that this is obviously a Lidar survey that happened before the, I think it's called the Las Colonias Slough was constructed. There was a side channel here, and actually this still exists. However, they extended it and kind of cut it through and made it come down this way. So, all right, I'm just going to refer to my steps real quick. So we created a 10. I have you guys, so there will be a write-up for this, and there's questions in here. So look for the italic prompts. So what is a 10? How does it use Lidar points to make it a continuous surface? And then the last step we did in class was convert the 10 to nodes. And so if you zoom into the 10 itself, remember 10 is a triangulated irregular network. So irregular just means there's no grid spacing. It's just a bunch of irregular points, which are the last data, right? If we bring in the last data, we can probably see that it's, the 10 is connecting all these Lidar dots, right? And we didn't have any data for the water itself, and so it just connects across the water. So our Lidar is the kind of nodes. Now we're going to, the next step is to go 10 to nodes, I think it's called. 10 node. Let me just double check. 10 to node. So it says exports the nodes. There we go. So it takes a 10 and then exports all those nodes. Now, why are we doing this? This is kind of a bit of a roundabout step because the last data is basically the node. So why don't we just convert the last data to point data? The way this works is we're creating ultimately what's called a terrain, and the terrain kind of needs the 10 type of data. And so this is just the steps we have to take to do it. So we made that 10 earlier from the Lidar data. We'll put that 10 in here. I don't really care about the name. I don't know what spot field is. Name the elevation attribute field. I think that's fine. So we'll run that, and what it'll do is just create XYZ points, which will be pretty similar to the last data. I'll zoom out and just see what it looks like. And you'll recall that when we created this 10 from the Lidar data, we used a shapefile to constrain it. We used the environment for that. Those steps should be in here as well. We created an area of interest shapefile, and then the 10 took the extent of that and basically clipped the 10 to that area. All right, there's all our bazillion points. I'm gonna just turn that off because we don't wanna, it takes forever to draw it. So now we basically have all the information we need from the 10. I'll zoom in just so we can kind of see that. So now we've taken all those nodes in the 10 and converted them to points, and these should be XYZ points. Take a look at the properties. Coordinate has Z values, yes, great. Okay, so these are 3D points. I'll turn it off again. All right, we'll turn that 10 off. I think I'll just keep the hill shade on. That's a little nicer easier to draw. Okay. Let's consult our steps. Now what we want to do, this is the kind of the critical step here. We want to remove the 10 nodes that fall within our survey boundary. And I made this, you are also welcome to make this. Basically what I did is I just connected the lines of our survey. And I said that those would, this would be the boundary within which our survey will be. So let's double check here. Here's our survey points. And so that's gonna work pretty well. In terms of the outer, these lines basically get the outer area. And then I have my survey area right here. So that's a polygon. And then I'll bring in these 10 points. So the way this works is we'll just select all the points that fall within that area. And I'll bring that area up just so we can see it. So here's the polygon that encompasses our survey points. And then we're going to select by location. And the input features are going to be the 10 nodes. That's what we want to select. We want them to intersect the selecting feature, which is the survey area. And we'll make a new selection. We're not going to, we don't need to do a search distance or anything like that, although you could have like a little bit of a buffer there. Okay, so now we've selected all those points that are within this survey area. That's what we wanted to delete because that's kind of like the old data from before the construction project. I'm gonna go to edit and I'm gonna do delete. And then let's deselect that. And we made a nice little hole in our TIN data. I'll save that. Now it's locked in. Okay, last step really. Now that we've created this TIN on the based on the ground points of the LiDAR data, we have converted that TIN to nodes, and we deleted the nodes within the area of our GPS survey. Now we're going to create the TIN one more time, and this time we're going to bring in the nodes, and we're also going to bring in the break lines that we made and the other survey data, because not all the survey points we took we made into break lines. So here's the tool. These are just kind of the basic steps. We're going to create TIN. So we'll go back to geoprocessing, create TIN. We'll give it a name. So we'll call it Las Colonias as built. We'll keep the same coordinate system as our nodes for now. We can always change it later. And then here's where we put in the input features, and we can kind of give it different types. So first we'll do the 10 nodes, and we remember we took the data out of there. The height field, shape Z, I'll assume that's what the height field is. The type, we'll just call it mass point. So it's just basically the same thing it did for the LiDAR data. It's just going to treat this as a points that we want to put the TIN network through. So that's one piece of data. Now we're going to add new data. We're going to do our break lines. There's a shape Z in there, and then we can choose what kind of line do we want this to be, a hard line, a soft line. I'm going to say hard line because we did a pretty good job of kind of tracing the toes and the tops of the banks and that sort of thing. I'm going to add another one, and that's going to be our survey point. So it's just called points. The height field again is the shape Z, and then that was automatically, whenever you have a 3D shape file, it creates an attribute field called shape Z, and then that we'll treat those as mass points as well. So we've got three different kinds of data. We have the original LiDAR data, which is now a TIN node. We have the break lines from the GPS data, and then we have the other points from our GPS data. And if you'll remember, these are the ones that Christian took in the channel where you don't have break lines. These are the ones that Kalisha took on the bank. I just did a top of bank break line, and then we'll have some points in here as well. It might make sense, and Kalisha could tell us if it makes sense to make these into break lines. And you could always do that, but you don't have to. All right, so let's run this. Let's see what we get. I think this is the 10 right here. Yep. Okay, so here's our 10, Las Colonias as built. I'm gonna take the hill shade off. And I'll take our, we can look. I'll take these points off just so we can kind of see them. So now you can see that this TIN's been updated, and we have a very nice channel survey that is part of it. And it's not perfect, right? You can kind of see there's some inconsistencies here. That's okay. It's not the end of the world. What I might have you guys do is like cut a cross section just to kind of see what the channel actually looks like in this tin, how it's been represented. But you can see that all these points have been connected, and so here's a bit of a bank line, and here's, you know, there's a kind of a break-in slope that Kalisha caught here. You can see the channel bottom. We got a rock. Is that something we want to include? Maybe not. That's okay in terms of the survey itself, or the terrain itself that we made. So you could always go back and remove that and run the tin tool again. But now we have an updated surface with that Lidar, or sorry, that GPS survey that you guys did. If we were to do a hydraulic model, for example, and say, okay, we're gonna update the channel and figure out, you know, if there's so many CFS in the main channel, how much is flowing in the side channel, we would obviously have to continue our survey all the way out to connect it upstream and then also connect it downstream. As you can see that we stopped at that big water feature. So now you've got a tin, you can use this. This is something that you can export to CAD. You could also create a DEM from this, and that's how this digital elevation model that we got off of the county was created. They created a tin and then sampled it to make it a gridded raster. So you can search for, I think, tin to raster. You can put this tin in, tell it the raster, what method do we want to do to sample? And then you can give it a cell size and say, okay, I want my cell size to be 10 by 10, either meters or feet. I could make it 3 by 3 or 1 by 1 or something like that. So you could have it have a different resolution depending on your data. So go back and take a look at this walkthrough. There's one thing that, so definitely start from the top because there's some questions that are going to be embedded in here. So I want to make sure you touch on those and for your write-up. And the other thing that we didn't do together, but that you can do on your own, is to go look at those experimental points, remember? Most surveys, you want to open and close the survey on the same point and just to check how much drift happened. So we did that on this little piece of plastic, if you'll recall. And what I want you guys to do is to calculate the error. Let's see here. Calculate the mean XYZ error. So for X, Y, and Z, or you could pull X and Y and then give me Z separately. What you'll do is go to view attribute table. And you've got easting, northing, and then elevation in here. So you use these three fields, easting, northing, and elevation, just for the experimental points. I'm just going to sort it by feature code. I guess it's alphabetical.
Could you select those points in the map and then
Yes.
just sort by selection?
Thank you. Great idea. You guys are already way ahead of me in GIS. So I just did select. I selected them spatially like Kalisha suggested. And then you can click on this. This is show all records, and then this is show selected records. And then what you could do, the easiest way, I think, is to, I don't know if you can just export the table. Let me see.
I think you right click on the feature layer and then like export features table sort of thing.
Okay. So I right click on the points, data, export table. And then that will, you can give it a name. You don't want it in a geodatabase. So I'm just going to do it this way. I'm going to just do output location. So it's in that folder. And then I'm going to call it experimental points. And then let's go see what it gave me. It gave me a database file, a .dbf, and that should be, you should be able to open that in Excel. I think I've already told Excel or told my computer that Excel should open this file. So if you don't get a little Excel icon at the DBF file, you can always just open Excel and find it and open it that way. Or right click and open it with Excel. So it'll create this database file. It's a little funky because the spacing of the columns is always weird. The first thing I always do when I open a DBF file is I click in this top corner right here, and that selects everything. And then I double click on this column line. You can see that the cursor goes to this little column kind of thing. If I double click, it'll just snap everything to meet the width of the data. So now I've got, because it's kind of hard to navigate a database file when it opens in Excel. So now I've got this, I can just calculate the mean error. And how do we define mean error? Because we don't know what the real value is, right? There's no like true value that we're comparing it to. How would you guys calculate the error here?
Would you get the average elevation out of those points and then do an error like for each point, compare it to that average, and then find an average error value for the whole elevation itself?
Yeah, that's great. So you could do the mean error from the, so you take the mean, right? So we'll just do average for easting. Okay. And so that's the average easting value. And then I would just take the difference of each one, like Christian said. And then I'll press F4 to kind of lock that in, function F4. And then so it'll always subtract it from that one column. Okay, great. And then what I can do is, so these are all the errors, the differences from the mean. And then what I can do is, I can do two things. One, I could take the average of these. And that's going to give me the overall mean error. But you'll note that this is super tiny, right? The negatives and the positives will cancel each other out, which is fine. And that's good to know. So this is the mean error. And it'll tell you, is there any bias, right? Is there any, like, are we more up or down or left or right? But you could also do mean absolute error. And what mean absolute error is we take absolutes. I'm going to take the absolute value of everything. I think that'll work. Yeah. What it does is it just takes everything and makes everything positive, the absolute value. And then it takes the average. And so that's going to be a little bit bigger. You can see that the mean error there, and I'm going to just take these digits out, is about 0.02 feet, mean absolute error. But if we average everything out, then it's really tiny. There's no bias, right? So you can do that for easting, northing, and elevation. I think root mean square, let me see, root.
You need SQRT for square root.
Oh, okay, yeah. I was just going to look up the formula for our root mean square error. Root mean square error. So it's the square of the deviations from the mean, the square root. So you square the deviations from the mean, and then you divide it by, I guess, n. So that's probably pretty close to the standard deviation. Oh, here we go. Mean square error. So it's just the difference between the mean squared. Okay. So another way you could do is root mean square error. So root mean square error. This is a little bit different because what it does is you take the difference between this and the mean. Or sorry, this is the error, right? So we're going to square all our errors. And then we're going to sum those up and then take the square root of them. So this is the root mean square. It's just a little bit of a different metric, and it kind of amplifies because you're squaring the differences. And then taking the square root, it kind of amplifies the bigger deviations. It's just a different way of estimating the error, and it's often something that's reported.
Hey Joel, so for those errors, do we have to divide them by the average that we had?
I don't think so. So what I did here is I just took each individual observation, I subtracted it from the mean, and then I took the average of those differences. If you wanted to do a percent error, Christian, you could do that.
Oh, that's for percent error, okay.
Yeah, and so for this case, we did the average of the absolute values, and so I could do mean absolute error 0.02 divided by the average. And so in terms of, well, you know what, though, that doesn't really make any sense because that's such a big number, right? And that number is kind of arbitrarily big because it's the easting value. And remember how we do a false easting and a false northing to kind of inflate the number so we never go into negative territory. So in this case, I don't think it really makes sense to do a percent error, if that makes sense.
Yeah, I was just confused because for error, we always divide by the total. So
yeah,
that's why I brought the question up.
I know what you're saying. Yeah, and then in this case, and it's just how error is kind of a vague term. And so we're going to say error in this case is the difference between each observation and the mean. So that's the, and if you look back at the walkthrough, that'll be in the first, I think that's in step 2. So just report that and write that up. So that's all I've got for today. We're done with the kind of Lidar GPS surveying portion. We'll spend the rest of the semester, or I guess the next probably like week and a half, doing some more analysis with digital elevation models. We'll do some hydrology work. We'll do some DM of difference where we subtract the 2 different surfaces between time periods and do some analysis with that. And then we'll get into photogrammetry and drone imagery and creating 3D models for the end of the semester. Any other homework questions or other general questions?